Hi, this is Barrett Givens, and in this video, we're going to talk about closed sets. So far in topology, we've learned about open sets, we've defined what a topology is, and we have talked about what a basis for a topology is. Now we're going to start talking about different types of sets and operations we can do with sets, but we're going to start with closed sets. So a definition, a set A in a topological space X is closed if and only if X complement is open. So a set is closed if its complement is open. And so let's just start with some examples. Let's start with some examples. Let's start with the standard topology, which is the topology in which open intervals form a basis. So any set is open if it can be written as a union of open intervals. And then I want to ask which of the following sets are closed. Okay. And you know what? I'm going to move this right up here to give myself a little bit more room. Okay. So let's start with the set capital A, which I will call negative infinity to negative 1 closed. Okay. So on a number line, this looks like everything below less than or equal to negative 1. So by the definition of closed, to see if a set is closed right now, using the definition, we would just have to look at A complement. So what is the complement of A? Well, that would be everything from 1 and above. And in the complement, sorry, not 1, negative 1. In the complement, negative 1 is not included because negative 1 is included in A. So therefore, it's not included in A complement. So A complement looks like this. Okay. And then you have to ask yourself, is A complement open? Can A complement be written as a union of open intervals? Yeah, I could write A complement as negative 1 union 0, union negative 1 union 1, union negative 1 union 2, and so on. It's an infinite union, but that's okay for open sets. And so this is open. And that tells me that negative infinity to negative 1 is closed. Okay, its complement is open, therefore it is closed. All right, what if I were to look at capital B? I'm going to say is the closed interval from 3 to open at 4. So let me draw a little number line and draw a picture. 3 to 4. And then I have to think about B complement. So B complement looks like everything from negative infinity to 3, but not including 3. Union, everything from 4 to infinity, but including 4. Since 4 is not in B, then 4 is in B complement. Okay, that's B complement. Is B complement open? Is B complement open? So certainly the negative infinity to 3 part is open. The same way up above, negative 1 to infinity was open, okay? When you have an interval with infinity or minus infinity at one end, and then the other end is not including the endpoint, that is an open set in the standard topology. What about the 4 to infinity? Is that open? I mean, you might think it's not because the point 4 is included, but let's think about why that is. What happens at the point 4? If I were to take the point 4 right here, I want to know, is B complement a neighborhood of that point? Is B complement a neighborhood of that point? So if I take the point 4 and I draw an open interval around it, does that open interval stay inside of B? Sorry, stay inside of B complement. Does that open interval stay inside of B complement? Not the way I drew it just now, right? Well, maybe I just need to make it smaller. Maybe I just need to zoom in and make it smaller. Does that open interval stay inside of B complement? No. No matter how small I make it, if I draw an open interval that has 4 inside of it, part of that open interval is going to have numbers less than 4. And so therefore, no open interval that I draw can stay inside of B complement, which means B complement is not a neighborhood of the point 4. B complement is not a neighborhood of the point 4. B complement is not a neighborhood of 4. And so therefore, B complement is not open. And that means that B is not closed. Okay? So we've seen one closed set and one not closed set. Let's do a couple more. How about if we do C? I'll let capital C be singleton pi. Then what is C complement? So capital C is just pi all by itself. So C complement should sort of be the opposite of that. So it's like the whole number line, but with pi taken out. So C complement looks like negative infinity to pi, open at pi, union pi to infinity, open at pi. C complement is open, and therefore C is closed. Okay, let's do a different topology now. Let's do a different topology now. Okay, so here's another example. What are the open sets? Sorry. What are the closed sets in the finite complement topology? On any set X? What are the closed sets in the finite complement topology? And let's just remind ourselves, what is the finite complement topology? Sets are open in the finite complement topology. If and only if either the set is empty set or the complement of the set is finite. Okay, so let's think about what a closed set would look like. Let's see if we can just start with a generic closed set and then kind of gradually work through what it would be saying about that set. So suppose F is closed. That would be true if and only if F complement is open, which would be true if and only if F complement equals the empty set, or the meaning of the finite complement topology is that a set is open if it's either empty set or its complement is finite. So the complement of F complement is finite, which would be true if and only if, well, what does it mean if F complement is the empty set? So if F complement is the empty set, that means there's nothing that's not in F. Nothing that's not in F. That means F has to be everything. F is the whole space. Okay. Or, and now what is F complement complement? If I take a set and I take its complement, that's like its opposite, and then I take the complement of that, I get back to the original set again. F is finite. So the closed sets are precisely those sets which are finite or the set X. Okay, so either the whole space has to be closed, and if you're not the whole space, then you just have to be a finite set to be closed. Okay, So in upcoming videos, we'll talk about some theorems and properties of closed sets, but for now, we just defined the definition of closed sets and did some examples. Thank you for listening.